Professor R. Ashokamani, Director for Research and Development, Dhanalakshmi Engineering College, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in Applied Electronics. Now, we are going through a course of lectures on crystal structure, which is intended for those who are going through the paper on physics of materials. In this lecture, the contents are rotational symmetry, reflection, inversion, rotoreflection, rotoinversion, incompatibility of 5-fold rotation and translation, and Bravais-statistics. I told you in the previous lecture about rotation symmetry, and we say that a body is have an n-fold rotational axis, provided it goes back to the same configuration n times when it is rotated through what angle? 360 degree. So, now you look at a square lattice. You got a square lattice. When it is rotated through 90 degrees, it goes to a lattice here, which is in no way different from this lattice. Okay. So, again rotation through 90 and so on. So, a square lattice, by now all of you know, will have a 4-fold rotation axis. An equilateral triangle will have a 3-fold rotation axis, whereas a square will have a 4-fold rotation axis. Okay. This is what I intend to say from this slide. Then you look at this diagram. Tell me what is the foldness of rotation. You see here a bird, if it is rotated through 90 degree, it will come here, right. Another 90 degree rotation will come to this place, right, and another 90 will go back here. So, therefore, this has got a 4-fold rotation axis. As far as the birds are concerned, you have got 4 birds. Whenever a bird is rotated through 90 degree, or this the pattern or the whole slide, when it is rotated through 90 degree with respect to this as the axis, right, perpendicular to the plane of slide. When I rotate it through 90 degree, you will go back to identical configuration. You do not know whether I have rotated or not. A 90 degree rotation will take back to the same configuration. So, it has got a 360 by 4 or 360 by 90 will be 4, right. It has got a 4-fold rotation axis. So, this system you got a square here. Now, this can be rotated, and you see you have a what you call a symmetry. Now, you should tell me what kind of symmetry is possessed by the word symmetry. It may be looking very funny. You see the word symmetry, we are talking about symmetry. What kind of symmetry is present in this word, symmetry itself? Now, this has got a 6-fold rotation axis, right. A hexagon obviously will have a 6-fold rotation. Now, what about this object? This object has got you got many sides, right, 1, 2, 3, 4, 5, 6, and you got many sides obviously this will not have a 6-4 rotation axis. A filled hexagon is used as a symbol for a 6-4 rotation axis. You have a hexagon, right? This is a hexagon 1, 2, 3, 4, 5, 6. So, a 6 sided element, it has got a 6-4 rotation axis. Now, I will pass on to an important geometrical proof, right? It is a very important geometrical proof. What I am going to prove from this mathematics is very important. Let us look at rotation in 2 dimensions. What I am now doing is, I consider a lattice, right. You have a lattice point here, lattice point here, lattice point here and so on. The distance that separates the 2 lattice points is A, right. This is important, right. The distance that is separating the 2 adjacent lattice points is A, right. Similarly, this distance also will be equal to A, right. This will be because it is a lattice. So, the distance that separates the adjacent lattice points should be the same A, right. Then look at a lattice point here, a lattice point here, this is a parallel plane, this is a plane here, right. This is another plane here or a line here, line lattice, there is another line lattice, it is a 2-dimensional lattice as a whole. Now, what I do now with respect to A prime, I rotate this A with respect to A prime, I rotate this through an angle phi. So, from this arrow now goes to this point, right, B prime. Do you understand this? I start from A prime, with A prime as center, I rotate this lattice vector through an angle phi, and let me assume that this ends with the lattice point B prime, right. Similarly, I do this anti-clockwise rotation, I do a clockwise rotation, right. With respect to A, I rotate, again you got this distance is A, with respect to A, I rotate this vector through an angle phi. Let me assume that I end up with another lattice point which I call B. The important point is this distance that separates A and A prime is A, right, obviously. Now, this line lattice, this is a 2-dimensional lattice. So, this line lattice and this line that I am having here, this line how do you obtain? B and B prime, rotation through angle phi, rotation through angle phi. The angle through which it is rotated, both of them are rotated, one in clockwise, the other is anti-clockwise, both of them are rotated through the same angle phi. Naturally, B B prime should be parallel to A prime, right. B B prime should be parallel to A prime, this is important. So, A prime is A, B B prime is again a line lattice, B is a lattice point, B prime is another lattice point. Obviously, B B prime should be an integral multiple of A, right. In a 2-dimensional lattice, these B B prime or RS and X y are parallel. So, naturally, B B prime should be integral multiple of A, there will be no confusion about it. B B prime should be integral multiple of A. So, what is the magnitude of B B prime? That is A prime plus A n plus A m. What is A n? If this is A n will be this is A, right. It is the horizontal component of A B prime. What is the horizontal component of A B prime? That is A cos phi. So, A prime n will be A cos phi. Similarly, A m also will be A cos phi. So, B B prime will be obviously A prime, that is A plus A cos phi and another A cos phi, that is 2 A cos phi. So, I write here B B prime to be equal to A prime plus 2 A cos phi plus another A cos phi here, right. Is it clear now? B B prime will be A prime or otherwise nothing but A, then plus 2 A cos phi. Okay. There should be no doubt regarding this equation, and B B prime, as I told you, should be integral multiple of A, right, because B B prime or RS and X y are parallel to each other, right. So, B B prime should be integral multiple of A. Therefore, m is an integer. So, B B prime will be m A, and what is A prime? I told you it is A, then you got 2 A cos phi. So, B B should be parallel to A, that is what I told you just now, that is a very important point, right. Now, 2 A cos phi you can cancel A throughout, right, A is common. 2 A cos phi or 2 cos phi will be m minus 1 by 2, right. 2 cos phi will be m minus 1 or cos phi will be m minus 1 by 2, right. M is an integer, m minus 1 should again be integer, right. Cos phi will be n by 2, where n is m minus 1, because m is an integer, n should also be an integer. Okay. What is cos phi? What are the values cos phi will take? You all know that cos phi will vary from plus 1 to minus 1. The 2 points which are to be now remembered are, you know very well, cos phi will vary from plus 1 to minus 1, and n is an integer, right, n is an integer. Now, these are the 2 points which are to be remembered, and what we have done is, we have been looking at a 2-dimensional lattice, and in the 2-dimensional lattice we have rotated this vector through an angle phi, this vector through an angle phi, and we end up with the B B prime, and this little bit of mathematics that we have done, it ends up with the equation cos phi to be equal to n by 2, and cos phi, you know the maximum minimum values, and n is integer, and let us go to this table which shows that n will take values minus 2 to plus 2. Then only, you know, cos phi will vary from minus 1 to plus 1. So, obviously, cos phi is n by 2. So, what are the n values? N will be taking values like minus 2, minus 1, 0, 1 and 2. So, that cos phi will vary from minus 1 to plus 1. Cos phi, you know, will vary from plus 1 to minus 1. Cos phi is n by 2. Therefore, the n values are varying from minus 2 to plus 2. Okay. If cos phi were minus 1, what is the value of phi? Cos 180 is minus 1, right. If cos phi is minus 1, what is the value of phi? It will be pi. If cos phi takes a value minus 1 by 2, what should be the value of phi? It is 2 pi by 3. By now, should be having a good knowledge on the basic trigonometry. So, your cos phi is 0 means phi should be pi by 2, okay, and half is pi by 3. If cos phi takes 1, then phi should be equal to 360. 360 is 0, right. So, rotation through 360 or no rotation is a null operation, right, no rotation or rotation through 360 or n times 360, both are the same. Okay. So, n is 2 pi by phi. What is n? N is the fullness of rotation. I told you earlier, how do you define rotation symmetry? Rotation symmetry, object is said to have a 4-fold rotation, provided, how do you get 4? 360 by 90. A object is said to have a 2-fold rotation axis, because 360 by 180. A rectangle will have a 2-fold rotation axis. A square will have a 4-fold rotation axis. Now, therefore, your n gives the fullness of rotation, right. So, what is n? N is 360 divided by 5. The 5 values are given here, right. 5 values. Now, from the simple mathematics that we had, in a 2-dimensional lattice, n will have values like this, n being given by 2 pi by phi, you have the 5 values are given here. So, if you substitute these 5 values, what you get is 180 degrees here, 2 pi by pi will be 2, 2 pi by 3 will be 3, and 2 pi by 2 will be 4, and so this kind of substitution of 5 values will give you n values. N is the fullness of rotation. What do you find here? You find the numbers 1, 2, 3, 4. What about 5? 5 is missing, right. You got 6, right. Note n is equal to phi is absent, right, n is equal to phi is absent, right. That is the important thing that I want to tell you with regard to possible rotational axis in 2 dimensions. What is the meaning of the fact that phi is absent? It means that pentagons cannot be used to fill up 2 dimensional space, or in other words, by stacking pentagons, you got a pentagon here, right, you got a pentagon here 1, 2, 3, 4, 5, a 5 sided element pentagon, right. By stacking pentagons side by side, you are stacking pentagons, right. When you try to stack pentagons side by side, what you find is, you find that there are empty spaces left. Okay. The sky blue areas represent unfilled space, right. There are empty spaces remaining here, or in other words, if I have pentagons 5 sided, you can take a sheet of paper, draw a pentagon. So, make 20 pentagons, put pentagons side by side, you will find that it is impossible for you to fill up the space, the 2 dimensional space. I am giving this area, I want you to put pentagon side by side. By putting pentagon side by side, you cannot fill up space, there will be some empty spaces left. On the other hand, if I give squares, you can fill up the entire space. Take the square lattice, you got a square here, translate the square, you get this square, you get a square here, translate, you come here and come here and so on. So, the entire space, a given area, can be filled up by stacking squares side by side. You can have square, translate the square. So, squares can be kept side by side, okay, one over the other or side by side, to fill up a 2 dimensional space. On the other hand, if you try to do the same thing with pentagons, you will find that it is impossible to have pentagons side by side without having some empty space. There will be some unfilled area, right. That is what you get from this mathematical proof. Supposing you rotate this vector E through 90 degree, and if you end up at a lattice point here, what do you understand? This phi will be 90 degrees, right, phi will be 90, 90 is allowed, 180 is allowed, pi by 2 90 is allowed, a 90 is allowed means the rotation axis will be 4. So, what I would like to tell you now, the incompatibility of rotation and translation of a pentagon. So, if you have an individual pentagon, remember the important point is, an individual pentagon, if you take this pentagon and with this as the axis, right, with this as the axis which is perpendicular to the plane of the diagram, with this with this center, I can rotate this pentagon, this individual pentagon, through what angle? 360 by 5, because it has got 5 sides. How much is the angle? 360 by 5 will be 72 degrees. If I rotate this pentagon about this as the axis, you will be getting the pentagon back. The individual pentagon will go back to the same configuration. The pentagon can be rotated through 72 degrees and I will be getting the pentagon back, but it is impossible to translate a pentagon. Okay, you have a pentagon here. If you translate a pentagon, you got this side. Where do you have this side? This side is not coming here, right? It has gone to this kind of right. So, this is the maximum that you can have with pentagons, right. In the case of square, you can have the things side by side. Okay, you have got a square here, then you have got a square here, you have the entire line. But on the other hand, here in the case of pentagons, you have got one side here, you do not have, you cannot place pentagons side by side. An individual pentagon can be rotated through 72 degrees. It has got an individual pentagon, no doubt, has got a 5-fold rotation axis, but stacking pentagons side by side is impossible, or in other words, it is impossible to translate pentagons and fill up 2-dimensional space. It is impossible to translate pentagons and try to see whether the two dimensional space is filled up or not. It is impossible to fill up two dimensional space by stacking pentagons side by side or by translating pentagons, right. So, it shows the incompatibility of a 5-fold rotation and translation. Okay. Similarly, if you look at 7-sided element 1, 2, 3, 4 the pentagon, right, then you can have 7-sided or 8-sided elements. If you put 7-sided objects and keep them side by side, what will happen is they will start overlapping. Similarly, 8-sided objects also will not be able to fill up space, there will be empty space here, right. So, in 2 dimensions the possible shapes, or you can have any shape, or you can have 2 refers to 180 degree. When do you have 180 degree rotation? This table will have 180 degree rotation, it is a rectangle, or 3 refers to an equilateral triangle, 4 refers to a square, 6 refers to what? A hexagon. So, the possible shapes in 2 dimensions, or to fill up a area, the possible shapes are, you can have a rectangle, that is a 4-fold, or an equilateral triangle, the 3-fold, a rectangle is 2-fold, an equilateral triangle is 3-fold, a square will be 4-fold, a hexagon will be 6-fold. Now, these are the possible shapes you can think of to fill up 2-dimensional space. Now, using the rotation symmetry, we showed that squares, equilateral triangles, hexagon and rectangles are the possible shapes using which 2-dimensional space can be filled up. Now, the question is, we have to think of a solids or 3-dimensional objects. Now, what are the, now our basic question is, now what are the possible shapes of unit cells, or what are the shapes that you can think of to fill up 3-dimensional space. I showed you the building of the College of Engineering Guindy or any other building. What are the shapes of the bricks? The brick can be parallel piped, the brick can be having a length, breadth and thickness, and so in solids, what are the shapes of unit cells? What are the values of A, B and C? What are the angles? You can have alpha, beta, gamma, that is the basic question. For that, we have to invoke, apart from rotation about which we have been talking about so far, we have to invoke the other symmetry operations such as mirror reflection. By mirror reflection, what I mean is, if you look at my body, if my combing is all right, right portion of my body is a mirror reflection of the left, provided I do not have scar or other things. My right side of the body is a mirror reflection of the left side. So, here the right side of the rectangle is a mirror reflection of the left and vice versa. Similarly, the bottom that you have here is a mirror reflection of the top and vice versa. The rectangle has got a mirror plane that runs vertically as well as horizontally, okay, a mirror reflection. Let us look at this object. Now, this system, human being, if you have got 4 legs and 4 hands, so you have got a mirror reflection, right. You see the 2 legs here, 2 legs here, 2 hands. So, these hands are the mirror reflection of these 2 hands, right. Now, let us look at other picture. Okay. You have the hand here, you can see the hand in the mirror, right, it is called a mirror reflection. So, look at this lady, right. Why has the line has been, why do you have a line? The line has been drawn and this lady has got mirror reflection, provided or as it happens that she has combed her hair, right. So, the line can be continued here, right, because the combing, if the center that has been taken here is on this side or this side, then the system does not have any mirror reflection. It has been, the combing has been done in such a way that you have the line here, the left hand side, the left side of her face is a mirror reflection of the right side and vice versa. Similarly, for this system again, you have the draw the line, the right is the mirror reflection of the left. Okay. This is the so called mirror reflection. Then you come across what is called a inversion operation. What is inversion operation? The rabbit has got the eye at some this is the origin, right, at minus x minus y, the 2 dimensional the plane, right, at minus x minus y. Then if the rabbit is here exactly along the diagonal, if the rabbit is found here, then there is mirror reflection. How do you define inversion? Inversion is a symmetry operation provided for every point x, y, z, that identical point at minus x minus y minus z. Now, you have to tell me, you take a cube, you look at the cube corner. Let us index the cube corner as x, y, z. Now, will you have a point at minus x minus y minus z? In the case of cube, it is possible, because a cube will have this kind of thing. So, this edge is the coordinates of this edge or x, y, z. Then for the cube, you go to this diagonally opposite corner, there will be again there will be a point here at minus x minus y minus z. Therefore, a cube will have inversion center, right. So, from the discussions that we had so far, in 2 dimensions there will be 5 possible lattices, right. So, the magnitudes are given here, this is one lattice, this is a unit cell. So, in 2 dimensions there will be 5 possible lattices. We have to find out how many lattice types are there in 3 dimensions. Now, let me summarize the lecture that I have given so far. Mirror reflection is a symmetry operation. What is inversion? Inversion takes every point from x, y, z to minus x minus y minus z. If that is so, then the object has got a inversion center, right. Pentagons when translated will not be able to fill up 2 dimensional space. You should understand this point clearly. There are 5 lattices in 2 dimensions. Let me now pass on to the question session. The questions are: what is meant by mirror reflection? How do you define inversion symmetry? Does an individual pentagon have 5-fold symmetry? Whether pentagons can fill up 2 dimensional space? If the above is not true, F-plane. How many lattice types are there in 2 dimensions? Let us look at the following pictures. What kind of symmetry is present in the following pictures? Look at this picture. This particular picture is very important, because in the lectures to come, or can you think of this picture and tell me what exactly you will be having along the x and y axis. The y axis here, x axis there. But where do you come across in material science this kind of picture, right? I will come to this picture again when I am going to one of the chapters which I will be dealing later, but the point is this picture should be remembered, right. This you would have come across earlier. Now, what about the symmetry of this picture, right? Butterfly, it has got a mirror reflection, the right is a mirror reflection of the left and so on, right. So, with this we come to the end of this lecture. The rest of the things we will see in the lectures to come. Thank you.